Problem number 37 and 38. That's the last problems for this competition. First problem from these two problems is looks like this. Massless elastic cord that obeys Hooke's law will break if the tension in the cord exceeds T maximum, unknown tension. One end of the cord is attached to a fixed point. The other is attached to an object of mass 3m. If a second smaller object of mass m moving at an initial speed v0, the larger mass and the two stick together, the cord will stretch and break, but the final kinetic energy of the two masses will be zero, so they will stop after break. If instead the two collide with a perfectly elastic one-dimensional collision, the cord will still break and the larger mass will move off with the initial speed of Vf. So we have F0, V final, we have object mass m, and we have object mass 3m. All motions occurs on a horizontal frictionless surface. So first question is, that's problem number 37. What is the ratio between V final and the V initial? So to solve this problem we need to do several steps. So first step is we have information that this cord will break for certain tension Tm, and it's obey Hooke law. It means that it will get some potential energy, and for this energy it will break. So in any case, if it will break, we are losing some certain amount of energy, and we can count what is this energy, because when these two masses have absolutely an elastic collision, it means that we can use momentum conservation and find what is new speed after they will stick together. So new speed will be 1/4 from initial speed of the first mass. After that we can count what is total kinetic energy after this collision, and all this energy will go to a potential energy for this cord before it will break. So it means that all this energy, K, equal 1/2 for m multiplied by 1/4 V0 square, which is 1/8 m V0 square. So we have this information about maximum possible potential energy for this cord, which we can use in a second step. So second step, we have absolutely elastic collision for two masses. One is moving and other is not moving. Good idea to know final formulas, just to memorize these final formulas, because we can use in many problems these formulas. What are the velocities for these masses after collision, after perfect elastic collision? This formula looks like this. V1 for the first mass, we have velocity is m1 minus m2 over m1 plus m2 v0, and v2 equal for the second mass, that's equal to m1 over m1 plus m2 v0. But if you don't remember these formulas, you can do very quick calculations to find them. Of course, we can use momentum conservation and energy conservation laws to find these velocities, but it's a long way. The shortcut is to use a new frame of reference, frame of reference for center of mass, and check what happened in this system. In this system, if we have two masses and immovable center of mass, they will go to this center of mass, collide here, and just rebound with the same speed, because we don't lose energy. So we just flip velocities, and after that we can go back to our initial frame of reference. Let's see. The velocity of this frame reference, v center of mass, that's equal, using momentum conservation, that will be m1 over m1 plus m2 v0. In this system, second mass moving to the left with this same velocity, but after collision it will change direction and it will go to the right with the same velocity. And when we are going back to our initial frame of reference, we just need to add to this new speed, new velocity, velocity of the center of mass, which is the same. So we have v2 equal to m1 over m1 plus m2 v0. For the first mass, we have speed, velocity in the center of mass will be v0 minus m1 over m1 plus m2 v0. That's a velocity of this first mass in the center of mass. After that it will flip, it will be negative, and we are going back to our initial frame of reference. We need to add the velocity of the center of mass, m1 over m1 plus m2 v0, which is finally equal m1 minus m2 over m1 plus m2 v0. So that's this one. Now we can use these formulas to count what is the speed, what is the velocity of this second mass after collision. We have v2 equal 2m1, which is m, over m plus 3m v0, which is 1/2 v0. That's the speed of our second mass. And we can count what is total kinetic energy of this mass. K2 equal 1/2 3m 1/2 v0 square, which is equal what is it, 3 over 8 m v0 square. Okay, that's kinetic energy right after collision. But when it will go with the cord, we extend the cord will get some potential energy before it breaks. And we know what is the potential energy for brake, so we need to just to subtract this energy. So that's a 1 over 8 m v0 square, which is 1 over 4 m v0 square. That's our kinetic energy after brake for the second mass. And now we can find what is final speed of this mass. That will be 1/2 3m over v final square, which is equal to 1 over 4 m v0 square. So now we see that v final equal 1 over root 6 v0, which is answer C, correct answer. Problem number 38. Find the ratio of the total kinetic energy of the system of two masses after the perfectly elastic collision and the cord has broken to the initial kinetic energy of the smallest mass prior to the collision. So we need to find what is K2, final kinetic energy, to initial kinetic energy. So from the first problem we already found how much energy do we lose for a cord break, this potential energy. That was P equal 1 over 8 m v0 square. And initial kinetic energy K1 was 1/2 m v0 square. So to find what is K2, we just need to subtract from K1 losing potential energy, which is 3 over 8 m v0 square, and finally K2 over K1 equal 3 over 4, which is answer D.